Hi guys, welcome back to Agora Math Circle's Mathcounts training. This is session 3 of our series. We'll be continuing what we learned in session 1 and 2. So go check those videos out if you haven't already. They're on our YouTube channel, so you might want to watch those. Then once you're done with that, come and start watching this one. And by the way, my name is Mugil Shanmugam. I'll be presenting this video. Alright guys, let's get into it. Session 3 topics. So today we'll be covering the following: Newton's little formula, integer solutions, part 1 and 2, and the principle of inclusion and exclusion. And underneath these topics, we have a few subtopics. For Newton's little formula, we have explanation and application problems. For integer solutions, we have formulas and sample problems. And for the principle of inclusion and exclusion, we have basic concepts and sample problems. So today, again, we're going to have a few of these formulas that you're going to have to know. Don't be too bothered about memorizing them because over time, naturally, they'll just come to you. For now, just be concerned with how you can apply these formulas to different problems when you're given them. All right, so let's get into it. So the first thing we're going to learn today is Newton's little formula. Newton's little formula is a useful formula to use when you're given a sequence and you're asked to find the next term, provided that the sequence goes by a few conditions. First, the sequence must have a stable constant k as the nth difference between terms. And I'll put a chart in there. So basically what this is saying is if they give you like a pattern, like 1, 2, 3, 4, 5, that's very simple. But sometimes you'll get more complex patterns. It's harder to find what the difference is and what the next number in the series is, or the sequence is. So in order to find what the next number in the sequence is, you can use this formula provided that the nth difference has a stable constant k as the value. By stable constant k, I mean that the difference between these terms, the nth terms, has to be a same constant, so like 1. Each time there's a difference of 1. As you can see in this chart down there, I have t plus 1, t plus 2, t plus 3, t plus 4. This is the number of terms. So t, let's just say that's the first term. T plus 1 is the second term. T plus 2 is the third term, and so on. Now, a is my first value. B is my second value. C is my third value. Now, down here, you can see this k. This k is going to be the difference, or my nth difference, and it's a stable constant. So as you can see, based on this, I can fill out the question marks in the chart. Because what happens is t plus 1 minus t will give me b. So this question mark minus a will give me b. And based on that, using that relationship, I can fill out this entire chart for myself. And when I'm done filling out the chart, eventually I'll reach a point at this bottom over here when I get the same number. It's going to repeat. Let's just say that k is 2. Then what's going to happen is I'm going to get a 2, a 2, a 2, and it's just going to keep repeating on the bottom line. That's when I know that I've reached the nth difference. So I need to count how many times it took me to reach this number, and that's going to be my k. So in the example I just gave, when you have 2 at the bottom, then 2 would be your k. And your nth difference in this case would be 1, 2, 3, 4. So based on that, you can calculate this and plug into the formula. So it's always very helpful to draw these charts because then you can use it in your formula. All right, here's another diagram of Newton's little formula. And so here what I've just done is I've given you the chart, but I've just plugged in 1 for t. So it's the same exact chart, but as you can see here, that we've expanded a little to show that k expands between each of these terms. So if 2 was at the bottom for each of these, then that's how you know that you've reached your stable constant k, when every single term at the bottom is equal. Right. So the formula for finding the nth term of any sequence goes as follows. A of n, which simply means the nth term, is equal to a into the combination of n minus t choose 0 plus b into n minus t choose 1 plus c into n minus t choose 2 plus so on until you get to k into n minus t choose m. And the formula for finding the sum of n terms, so that was for finding the nth term. If they give you a problem like find the 7th term of this sequence, then you use that formula. But now the formula down here, you can see that formula is the formula I'm going to use when they ask me to find the sum of a sequence. And this will be found by using n choose 0, that's the first, times 0 plus n choose 1 times a plus n choose 2 plus b, n choose 2 times b plus n choose 3 times c plus so on till you get to n choose m plus 1 times k. So now this choose notation may be confusing you, and we'll be going over that shortly with combinations. So combinations is actually a later topic we'll go over in math counts. For today, I'll just be like briefly telling you how you can use a formula to solve this, but we'll go in depth into what it exactly means in later sessions. But those are just two different formulas that you can use when you're given a sequence and asked to find either your nth term or your sum. And the other thing that I forgot to mention here is for these two formulas to work, you want to have that chart written out, the chart on the previous slide. This chart, you want to draw it out for these problems so you can figure out what your A is, what your B is, what your C is, what your K is, and what your M is. Only if you know these 5 things, you will be able to solve your equation. Okay, and explanation of combinations. So for combinations, basically it's just the number of ways to choose this number of things out of the total number. So when you see x is equal to this weird parentheses and one number over the other, this means a combination. Or you can also represent it as 10 choose 2. So we're discussing the ways in which out of these 10 numbers, we can choose 2 numbers. To figure out the combination of anything, we use this formula down here. So the combination of anything is equal to the top number, so that's n generally, n factorial over r factorial into n minus r factorial. So as you can see, when we want to find the combination of 10 and 2, it's simply 10 factorial over 2 factorial into 10 minus 2 factorial. And when we calculate that out, we get 45. In case you don't know what a factorial is, I went over what those are in session 2 video, so go check that out in case you don't know what this is. But a brief definition here, a factorial is basically when you multiply by every single number that is less than it. So 5 factorial is 5 times 4 times 3 times 2 times 1 and so on. All right, so you can use this formula down here, I've shown it, n factorial into r factorial, n minus r factorial. So in the previous formula, you can see that we have a lot of combinations here, n minus t and 0. So you'd simply just plug this into the formula for combinations, and that's how you would solve it. All right. So this is a sample problems for Newton's third formula. This is the first video of mine that you're watching. We usually have a format for these where I'll read the problem and maybe give you a hint if this problem requires one. Then after that, I'm going to ask you guys to pause the video, go ahead and solve this on a piece of paper or wherever you solve your problems. Then resume the video and I'll go over the solution. Okay, so I'll read the problem for you guys. Find the 6th term of the following sequence. 2, 6, 22, 56, 114. This one shouldn't be too complicated. All you're doing is plugging it into that formula that we learned for the nth term. But make sure to draw the diagram first because that's going to be very helpful. Okay guys, pause the video and go ahead and solve this. Okay, hopefully you guys paused the video, solved it, and did whatever you need to do. So let's get into the solution. Consider the following diagram. I know that might be a little hard to see, but I showed it to you guys there. I drew out the diagram. So off the top, you can see this 1, 2, 3, 4, 5. That's the term. So first term, second term, third term, fourth term, fifth term, so on. Now the 2, 6, 22, 56, 114, what that's telling me is that's the terms that were given in the sequence. The sequence told us the terms were 2, 6, 22, 56, 114, so I wrote them on the top row. Now I gotta start calculating. 6 minus 2 gives me 4. That's what I wrote down here. 22 minus 6 gives me 16. 56 minus 22 gives me 34. 114 minus 56 gives me 58. So I've calculated my second row. This is my first difference. Now I need to calculate my second difference. To do that, I subtract all the numbers in the second row right now. So 16 minus 4 is 12. 34 minus 16 is 18. 58 minus 34 is 24. So I just found all the terms in my second difference sequence. Now that I have my second sequence, now I can try to find the third difference if there is any. So when I do that, 18 minus 12 gives me 6, and 24 minus 18 gives me 6. So if you're following my mouse right there, I just showed how you get down to this constant difference of 6. You can see here that it's 6 on the bottom, another 6, and if we expanded this, we would see that there's a bunch more 6s on the bottom row. So now what we need to do is, which of the differences gave me this constant number of 6? Well, the first difference was 4, 16, 34, 58. The second difference was 12, 18, 24. So clearly the third difference will give me my 6 and 6. So that means my m is equal to 3. and the k is the constant difference, which is 6. Now you can find your a, b, and c based on that earlier diagram. I'm going to quickly go back to it right here, a, b, and c. So using that, we can find where a, b, and c in this diagram are. My a, and b, and c is going to be 2, 4, and 12. Okay, so now that we found all our terms, we can just plug into the formula now. Right here, I've written out a is equal to 2, b is equal to 4, c is equal to 12, k is equal to 6, m is equal to 3. Now we can just plug everything we know into our formula for n equal to 6. The reason we're plugging it in for n equal to 6 is because we're trying to find the 6th term of our sequence. Remember, if we scroll back, it says the 6th term, nth term, 6th term. So basically they're asking you for n equal to 6. So simply just plug that into your formula along with whatever else we found. And when you plug all that in, you can solve all this using our combination formulas and multiplication. And at the end, you'll get 202. So our answer for this one is 202. The 6th term of the sequence is 202. So that one was pretty simple. It's just simply taking that formula, drawing out your diagram to find all your terms, and then plugging everything you know into that formula. Okay, let's move on to our second topic for today, integer solutions. So this is part 1 of integer solutions because integer solutions actually has a lot to cover. It covers many different types of problems, so that's why this is a little long of a topic and there's many formulas, but it'll be very helpful because this can deal with like many problems that you'll get on the math counts, and you can simply just apply a formula and it'll be done. So for these types of problems, you always want to let n and r be two positive integers. So n and r will always be in your formulas, and they're just simply two positive integers. For the equation x plus 1, x plus 2, x plus 3, so on until you get x plus n, and you have n terms, nr, then the number of positive integer solutions is n is equal to n minus 1, r minus 1. For the same equation, the number of non-negative integer solutions is n plus r minus 1, r minus 1. So the difference between positive integer solutions and non-negative integer solutions is when you say non-negative integer solutions, you're including 0 in your solution possibility. But you're not doing that when you say positive integer solutions. So that's why we need this extra -1 back here. And this got cut off a little, but it was x and subscript n, and it's just n at the end. It was n, x subscript r equal to n. Okay. So for the following problems, we operate on the premise that x of I, so the x of any value is greater than or equal to 1, but less than or equal to 6. So the number of positive integer solutions is n is equal to n minus 1, r minus 1, so n minus 1 choose r minus 1, minus r choose 1, into n minus 1 times 6 minus 1 choose r minus 1, plus r choose 2, into n minus 2 times 6 minus 1 choose r minus 1, minus r choose 3 into n minus 3 times 6 minus 1 choose r minus 1, and so on. So again, that was a mouthful to say, but what I'm basically saying is you're going to be expanding that original formula and adding in all your numbers for this new constraint we just got, that x has to be greater than or equal to 1, but less than or equal to 6. And based on that, this may seem complicated, but it's not that hard since you just have to plug it into the combination formula for each one. So now there's a different type of problem that the same situation or the same formula will apply to. Another type of formula or situation we're often given is they'll ask us how many ways can you roll the sum n with 3 dice. And you can expand this similarly for getting a sum of n with 4 dice, a sum of n with 5 dice, a sum of n with 6 dice, a sum of n with 7 dice, and so on. So here, as you can see, our formula is going to be n is equal to n minus 1 choose 2, 3 minus 1 is 2. So n minus 1 choose 2, minus 3 choose 1, into n minus 1 times 6 minus 1 choose 3 minus 1, plus 3 choose 2, into n minus 2 times 6 minus 1 choose 3 minus 1. So that was a lot of choosing, but what I'm basically saying is for all of these parentheses, we're going to be using our combination formula, our factorial formula. Once we plug all that in, then we'll be able to simply just multiply and subtract our whole thing. And this is the number of ways to roll a sum of n with 3 dice. And n, again, capital letter N, I went over this in the previous video, but whenever I use capital letter N, I'm simply referring to the number of ways to do something, the number of ways to walk, the number of ways to create a triangle, the number of ways to roll a sum of n with 3 dice, and so on. So the same thing we can expand this similarly for more dice, right? So again, if it was, let's just say 4 dice, then wherever you see 3, you'd replace it with 4, and you'd add a new category after the last expression saying 4 choose 3 into n minus 3, so on. So as you can see, it shouldn't be too hard, and you can expand this up to 5 dice. You're simply adding one more expression to your equation each time you're increasing a dice. For the number of 3-digit numbers with the sum of digits equal to n. So for example, if you have a number 111, so that's 111 in the digits, right? When you add that up, you get 3. So in this case, your n is 3. And they'll ask you, how many 3-digit numbers are there that add up to have a sum of 16 or something like that. So for this, what you need to do is you'd use this formula. Our restrictions are x1 is less than or equal to 9 but greater than or equal to 1. For x2 and x3, the restrictions are greater than or equal to 0 but less than or equal to 9. And our n is equal to n1 plus n2. So from here on, we're going to have a divergence in formulas. Basically, we're going to have to find our n1 and n2 separately, and when we add them up, we get the total number of ways to do something. And so for this one, when I say restrictions, I'm simply talking x1, x2, and x3. They're the different terms in our sequence that we're going to be calculating, and for this, they each have their own restrictions. As you can see, here you have your formula. This is for n1. So n2, it's not a lot of work. It's simply the number of solutions containing zeros in the 10 or unit place. So how we'd figure that out? You'd simply just list it out, right? So it has to contain a 0 in the tens or unit place. That shouldn't be too hard to find. Just list out the 3-digit numbers with that category, and then you can count them up. That's a just quick way to do it. It's much quicker than using any formula. But for n1, we'd actually use a formula. So for n1, it's equal to, right here you can see, n minus 1 choose 2, minus 3 choose 1, into n minus 1 times 9 minus 1 choose 2, plus 3 choose 2 into n minus 2 times 9 minus 1 choose 2. Again, so this is just a lot of choosing. We're doing a lot of combinations, but it's not too hard to evaluate these. We just plug it into our combination formula, and then we can just multiply everything together. So here, the thing is that once you figure this out, you only have your n1. So don't stop here. Once you find your n1, you need to make sure to go back, find your n2, and then add them together to get the total number or your answer. But in a similar situation, but for an r-digit number, so by r-digit number, I mean it could be 7-digit, 8-digit, 9-digit, 10-digit, whatever, right? You can apply similar restrictions to your x1 and your x2 and your x3. So if we go back here, we see our restrictions, right? x1 is less than or equal to 9, but greater than or equal to 1. For x2 and x3, the restrictions are greater than or equal to 0, but less than or equal to 9. So similar restrictions will apply when you do it with r-digit numbers. For again, we're going to have a divergence here. Our n, the number of ways, is going to be split into 2. Our n1 and our n2. Our n1 are the non-negative solutions to your equation using x, and n2 are the non-negative solutions for the same equation, but you use y and s instead of your x and r. So basically, you're making a new equation for your n2, solving that, and you have your original x equation for your n1, and you're solving that. Then you're going to add everything together. So I have the formulas on the next page. For n1, as you can see, I wrote it up here. It's n plus r minus 1, choose r minus 1, minus r choose 1, n plus r minus 1 times 10 minus 1 choose 2, plus r choose 2 into n plus r minus 2 times 10 minus 1 choose 2, minus so on. So you're just going to keep expanding that until you get the r, whatever your r is. So if your r is like 9, you're going to go until r choose 8. If your r is 10, then you're going to go until r choose 9, and so on. And then for n2, you can see it's the same exact formula, except the one big change is I'm using an s instead of an r. So as I told you, when I use y, I'm going to change my sum to s instead of r, and because of that, now I'm going to have this difference. I'm going to have s instead of r. So if you memorize the formula for n1 or you learn the formula for n1, however you do it, then basically you're given the formula for n2. You're simply just going to have s minus 1 chosen from every single option you have here. So that should be pretty simple, and you're just substituting r and s. Okay, so here we have a sample problem. This one is simple. So if you see the r-digit problems, You're generally not going to get one too complex with like 10 digit or 11 digit. It's usually just going to be a 3 digit or a smaller number, so don't be too worried about that. Okay, so here's our sample problem. 3 friends have a total of 6 identical pencils, and each friend has at least 1 pencil. In how many ways can this scenario happen? And this is from the 2004 AMCA. Okay, so go ahead, pause the video, and you can solve this one. This one is pretty simple. You just need to use that formula we learned at the very beginning, the one about the number of integer solutions to an equation. Okay, so go ahead and pause it. Alright, I hope you guys tried it, so let's go into the solution for this one. We need to use our formula for the number of positive integer solutions. So if I go back a few slides, all the way back here, you can see my formula, x1 plus x2 plus x3 plus so on until I get to x to the subscript r is equal to n. So that's my formula that I'm given here, right? So now I simply need to adapt it based on the problem I'm given. So if I scroll back here, my problem that I'm given only gives me 3 friends in my entire problem. So that means I only need x1, x2, and x3 is equal to n. N is the sum. Here, our sum, well, it says that there's 6 identical pencils. So x1 plus x2 plus x3. x1 is the number of pencils the first girl has, x2 is the number of pencils the second girl has, and x3 is the number of pencils the third girl has. When I add all these up, I'm going to get my sum of n, which is simply equal to 6. And my r is the last term in my x sequence. Remember, when we look back at the positive integer solution example in the formula, we found that our formula is x1 plus x2 plus so on until you get to xr. So here, our xr, the last x term, is x to the subscript 3, which means r is equal to 3. So our n is equal to 6, r is equal to 3. Now you can simply just plug into our formula. N minus 1, r minus 1, well that's 6 minus 1, 3 minus 1. In the end, we're going to end up with 5 choose 2. Now you can plug that into the combination formula using factorials, and when we do that, we get 10. So this 10 tells us that there's 10 ways for this to occur. So this distribution of pencils, so every friend has at least 1 pencil, can occur in 10 different ways. Okay, so now let's move on to integer solutions part 2. Part 1 mainly dealt with lots of combinations, and it was more about like how many ways can something happen. This is going to be more about solutions to an equation. So the number of distinct pairs of positive xy solutions for the equation 1 over x plus 1 over y is equal to 1 over n is n is equal to d into n squared, where d is the number of factors of n squared. So what they're telling us here is we have an equation. 1 over x plus 1 over y is equal to 1 over n. And the number of distinct pairs, so the number of solutions for this equation, are going to be given by d into n squared. So n squared, you're simply taking the denominator and squaring it, and d is the number of factors for this n squared. For when x is not equal to y, the formula will change to d into n squared minus 1. And the number of ways to express 1 over n as a sum of 1 over a and 1 over b is given by this weird notation, a d over 2, inside these half brackets. So basically the half brackets, whenever you see them, the first thing you want to notice with these is which way that they have the top. If you can look at the one I'm showing right now, you can see that they have this small little line on top of their brackets on the top. They don't have anything on the bottom. This means if it's on the top, it's a ceiling. If it's on the bottom, it's a floor. That shouldn't be too hard to remember because obviously on the top you have the ceiling and on the bottom you have the floor. So basically what this is saying is that I'm going to find my d over 2 and then I'm going to plug it into a ceiling function. Ceiling function means I simply find the biggest integer that's closest to it. So the ceiling function of 2.7 will ask 3. 3 is the biggest number that's closest to it, the biggest integer that's closest to it. So based on that, that's how I will evaluate my ceiling function. So the number of ways to express 1 over n as the sum of 1 over a and 1 over b is the ceiling function d over 2. And when you solve for x and y in this equation, 1 over x plus 1 over y equal 1 over n, you get x is equal to ny over y minus n. So the way they got this was they simply just did linear equations and they solved it like normal, except they don't know any of the values. So when you do that, you'll get x is equal to ny over y minus 1. You can also rewrite that as n plus n squared over y minus n. Whichever one will help you solve. So for different problems, you'll be given different pieces of information, So simply use the formula that's going to allow you to solve the easiest. And here, y minus n is a factor of n squared. So if y minus n is a factor of n squared, if you watched my first video, you should know that n squared will be divisible perfectly by y minus n. Okay, so for the same situation with m less than n, so before we were dealing with m not equal to n or m equal to n, but here with m less than n, our formula will change to x is equal to ny over my minus n, and my minus n is a factor of n squared. So again, that's just the formula. This one we derived from the previous one, except we simply have the condition that m is less than n, so based on that we were able to adapt our formula. So including a new variable. For 1 over x plus 1 over y plus 1 over z is equal to m over n, this is just an inclusion of the variable z. Before we only had 1 over x plus 1 over y, now we have 1 over z too. And if we know that m is less than n, we can determine the range of x if the following condition holds true. If x is less than or equal to y, and y is less than or equal to z, I wrote it out right here, then you can figure out the range of x to be the ceiling function of n over m is less than or equal to x, which is less than or equal to the ceiling function of 3n over m. So now n and m, as you can see, they're simply just the numbers in this fraction that our whole equation is equal to. So you can plug that in to find your range of x. After finding this, we can switch our equation to 1 over y plus 1 over z is equal to m over n minus 1 over z. So they didn't do anything fancy here. They simply took this 1 over z, subtracted it from both sides. So now you get 1 over y plus 1 over z is equal to m over n minus 1 over x. And using this, now we can solve it normally because there's only two variables on each side. So we can simply solve it using our previous equation. And here's some other quick formulas you want to know when you're solving these integer solutions. So the first one is 1 over n into n plus k is equal to 1 over k into 1 over n minus 1 over n plus k. And assume k is just a positive integer. 1 over mn is equal to 1 over n minus m into 1 over m minus 1 over n. So this is an expansion formula. If you have 1 over 12, you could split it up into 1 over 2 times 6, and then you can plug it into this formula and keep expanding it if you want to solve something. Similarly, here we have 1 over n minus 1, n plus 1, which is the difference of squares, is going to give us 1 half into 1 into n minus 1, 1 minus 1 over n plus 1. So this is helpful if you have a difference of squares and you're looking to kind of split it up a little more. 1 over n is equal to 1 over 2n plus 1 over 2n. So again, that's another helpful formula you can use to split up your equation further. And 1 over n into n plus 1 is equal to 1 over n minus 1 over n plus 1. So again, most of these are when you're given a single fraction, you can expand it using these formulas. Okay, so here's our sample problem. How many distinct pairs of possible positive integers m and n? So if m and n are confusing to you, simply substitute with x and y. Are there so that the sum of the reciprocals of m and n is 1/4? And this is from the state team round of Mathcounts in 1996. So go ahead, pause the video, and try to solve this problem. This one is a little complicated, but it's not too hard. Okay, hopefully you guys attempted to solve the problem. Now I'm going to go ahead and show you guys the solution. Okay, so if the sum of the reciprocals is 1/4, then the sum is 4. Because remember, it's 1 over x plus 1 over y is equal to 1 over n. So if I know that 1 over n is equal to 1 over 4, then n is equal to 4. This means that n squared, or s squared in this case, is equal to 16. So if you go back all the way back here, you can see that our formula is going to be d into n squared, and we know that our n is equal to 4, because this was 1/4, therefore n is equal to 4, and 4 squared is equal to 16. So if we know that 4 squared is equal to 16, now we just need to find how many factors 16 has. 16 has 5 factors, so our d is equal to 5. Therefore, there are 5 different ways, possible distinct pairs to satisfy this condition. So if you look here, there are many different ways to do this, but this is a simple way to do it, is simply you find your n, or your s in this case, and then based on that you can find the number of factors, and this is the number of possible distinct pairs that satisfy this condition, and the condition is that the sum of the reciprocals of m and n is 1/4. So here the reason why many people will get confused is because instead of x and y, they've given you m and n. So you could simply substitute this with x and y if that helps you solve it a little better. But at the end, you get 5 possible distinct pairs. There's other ways to do this involving factors, but this is just the easiest way to do it. Okay, let's move on to the next one. This is our final topic for today, and it's the principle of inclusion and exclusion. So we've already been exposed to the ceiling function, which is when the lines are on top. But when the lines are on the bottom, then we get the floor function. As you can see, I have a weird bracket here with lines on the bottom, which is our floor function. So this simply means that we take the greatest integer that is less than x. So if x is 2.1, what's the greatest integer that's less than x? It's 2. So that's how we'd figure this out. Essentially, it's like a weird way of rounding. And using this, we can find the number of positive integers from 1 to n that are divisible by d. And that's given by the floor function of n over d. And for the number of positive integers less than n that are divisible by d, then it's n minus 1 over d. So as you can see, both these are very similar, except one is just anything less than n, while the other is from 1 to n. And again, for both of these, we figure out what it is by doing n over d, and then we need to make sure to take the floor function of it. So here we're also going to go over intersection and union of sets. So usually when we discuss sets, we like to use Venn diagrams because they're easiest to understand. And this falls under statistics in general. So the intersection of sets is denoted by a weird u, so like an upside down u, b. And this basically just means a intersection b. And this refers to the shared values between a and b, or the overlap region in a Venn diagram. So if you could look at this little image I put down here, you have your diagram, your Venn diagram a and b, right? So now you have this a and b, and the intersection region, that's going to be your a union b, the overlap or the shaded region in between. Now if you have a, b, and c and you want to find the intersection of them all, it's the shaded region that they all share in the center. The union of sets is denoted by a u, and a b. Not exactly a u, but that's just easiest how you can visualize it. And it refers to all the values belonging to the a or the b circle. This would be like the entire Venn diagram. So as you can see, a union b down here is simply both circles. Even the intersection region is also included in a union b. Anything in either the circle A or either the circle B or in both circles is all included in a union B. Finally, A union B union C, it's everything in that circle. So anything inside those circles, even if it's in the intersection region, it's all included in this A union B. So here I say the entire Venn diagram, but if there's something that's outside of the circles, then it doesn't count. So here are some formulas that you can use for the union of 2 sets and 3 sets respectively. So the first one, if you have n, A union B, you can split it up into n into A plus n into B minus n into A intersection B. So sometimes you don't want to find the union, but you know what the intersection is, so then you can just plug it into this formula. Similarly, for n of A union B union C, you can split it up into n into A plus n into B plus n into C minus n into A intersection B minus n into B intersection C minus n into C intersection A plus n into A intersection B intersection C. So basically what we're doing here is we have this union, and the union is asking us to find everything that's contained in these 3 circles. But instead what we're going to do is we're going to break it up so that we only need to find the number of dots in each circle, and then we simply minus and subtract the different the different intersections of these different circles so we can get the final answer. So again, back here, this is our A union B union C, but we can also represent that as this formula right down here if it's multiplied by n. Okay, so now let's move on to a more expanded formula. So you should have noticed a pattern here. We're basically just expanding this formula each time when we add a new circle. So here we're going to add a D circle, and I'm not going to read out this whole formula because then I'd be out of breath, but basically you can read it. I'll stay on the slide for a little and I'll explain it. So basically here we have 4 sets. That means there's 4 circles in a Venn diagram, and we're trying to find the union of all of them. So everything contained in these 4 circles. Now to figure that out, we go with our original formula, but each time, usually we just did A, B, and C when we did our union part. Now we're simply going to add in our D part, so even when we're doing unions, and later when we expand it in our intersections, we're also going to need to include this D here whenever we're doing it. And essentially, as you can see here, we're basically splitting it up, so we're going to do the intersection of A and B, then we're doing the intersection of B and C, then we're doing the intersection of B and D, and we're basically doing every single possibility of 2 circles, finding their intersections, then doing it of 3 circles, so like A, B, and C, or A, B, and D, and then finally we're taking the intersection of everything, and when we add that with our n times A, n times B, and n times C, then enter n times D, then finally we're going to get our n into A union B, union C, union D. So again, this is complicated, and it's very rare that you're going to see this. It's just handy to know. But basically what we're doing again is we're breaking up this big circle into many small circles and small values that we can add up and subtract to get our final answer. Okay, so this is our sample problem. Obviously, I'm not going to give you guys one of the ones where we have to use the entire A, B, C, and D, because that's very rare. But be ready to use formulas up to A, B, and C. So for this one, it says, how many 3-digit numbers are divisible by 13? And this is from the 2005 AMCA. Alright, so again, for this one, we'd simply use one of the more basic formulas we learned. We learned the floor function, so it's one of the formulas that's related to that. So based on that, you should be able to figure this out. So go ahead, pause the video, and give this problem a go. Okay, hopefully you guys solved the problem, so let's go ahead and look at the solution for this one. So for this problem, we can use the formula we learned to find the number of numbers less than 999 that are divisible by 13. So that would fulfill our problem because it says how many 3-digit numbers are divisible by 13. So anything less than 999 would work. But it only says 3-digit numbers. So it has to be greater than 99 and less than 999. So based on that, we need to subtract those which are less than or equal to 99. So as you can see here, I've wrote it out using the formula. So the first one says floor function of n over d. And for this one, we're trying to find it for 999. So 999 over 13, and the floor function of this is going to give you 76. And now you would do the same thing, but this time for 99. So n over d, the floor function of this, is going to be the floor function of 99 over 13, which is going to be 7. So now we know the number of from 999 to 1, how many numbers are divisible by 13, and we also know how many numbers are divisible by 13 from 99 to 1. So when we subtract this number of numbers that are from 99 to 1 and are divisible, then we'll get 76 minus 7 is equal to 69. So again, what we did was we found the number of integers from 999 to 1 that are divisible by 13, but that doesn't give us all 3-digit numbers because it also includes 2-digit numbers. So then we subtracted all the 2-digit numbers out, and that's how we got 69 in the end as our answer. So that one was a 2-step one. Many people will go straight for the 999 and they'll find 76, then they'll leave it there. But you want to remember to subtract out the 2-digit numbers so you get only the 3-digit numbers. So again, that's why you want to read the question very carefully. So yeah, our answer for that one is 69. Okay guys, thank you so much for watching the video. I hope you enjoyed it. Please like and subscribe to our channel if you enjoyed the video, and leave a comment with any questions, or email info@agoramathcircle.org if you have any questions. Thanks for watching. Have a nice day. Bye.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramathcircle.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email, but without the info and the end. So bye!